In this video, we are going to study this function here, fa, and fa depends on a parameter a, which is chosen in the real line r, and you see that this function is defined by pieces, so it's a piecewise defined function. It's defined in this way here for x smaller than 1/2, it's defined 0 in 1/2, and it's defined in this way here for x bigger than 1/2. So now the question is, when is this function continuous? So in other words, we have to find the values of a for which fa is continuous. So first of all, let's try to understand what it means. If you look at it, for x smaller than 1/2, the function is certainly continuous and very simple. For x bigger than 1/2, the same. So everything boils down to studying the case x equal 1/2. So let's draw only a qualitative graph of this function to try to understand what's going on. So here, suppose we have 1/2. Now in 1/2, we know that the function is 0. So the function is here. So for x smaller than 1/2, we have a parabola. So let's suppose it's something like this. And for x bigger than 1/2, we have another function. It doesn't really matter the exact shape of this function. Suppose it does something like this. It doesn't really matter. We don't know yet. We'll find out. So you see that in order for this function to be continuous, it's enough to study these two limits for x going to 1/2 from the left and from the right, and we need to make sure that these two limits are both equal to 0. Okay, so now let's try to be precise, to write this argument precisely. So we have that fa is continuous, and if I don't write where, it means over the whole domain of fa, so over the real line, if and only if fa is continuous in 1/2, if and only if. So as I said before, the continuity in 1/2 means that these two limits have to coincide, and they have to coincide with the value in 1/2. So if and only if the limit as x goes to 1/2 from the left of fa is equal to fa of 1/2, and this has to coincide with the limit as x goes to 1/2 from the right of fa of x. Right, perfect. Now we already know that fa of 1/2 is 0, just by definition, and so this is still equivalent to requiring that these two limits coincide and that they are 0. Right, so now we only have to study to calculate these two limits. So let's do it. You'll see it's not that complicated. So let's start with the easy one, which is the one from the left. Because you see from the left, the function is much simpler. So the limit as x goes to 1/2 from the left of fa of x, we just now write the expression for fa. Right, here it is. Here you see I can remove the left, the minus sign, because this function is continuous over the whole real line, so this doesn't really matter. Right, now this function is continuous, so I just have to replace x with 1/2. So this gives me 2a 1/4 plus a minus 2 1/2 plus a squared over 2, right? So now this gives me a over 2 plus a squared over 2 minus a plus a squared over 2. This is nothing but a squared minus a over 2, namely a times a minus 1/2. So this is the easy limit, the limit from the left. So the limit as x goes to 1/2 from the right of fa of x, this is equal to the limit as x goes to 1/2 of this expression here. And now we need to calculate this limit. Now you already see that this function doesn't depend on a at all. So we just need to be lucky. Being lucky here means that we hope that this limit is 0. Otherwise, there is no hope for this function fa to be continuous. So let's calculate this limit. So first of all, you see that both the numerator and the denominator go to 0. Why? Because in the numerator we have sine of pi over 2, which is 1, so 1 minus 1, 0. And in the denominator we have 2 times 1/4 is 1 half plus 1 half 1, and the log of 1 is 0 too. So we have 0, 0, and we cannot conclude immediately the value of this limit. So we have to work harder to find it. So the first observation, thinking about the sign, so let me just draw it here very briefly. The sign here is calculated in pi over 2, so the sine pi over 2 is here, and we don't remember a known limit on the sine in pi over 2. However, we do remember a known limit for the cosine is 0, but the cosine in 0, you see, is nothing but the sine translated by pi over 2. So it's useful here to recall a trigonometric identity to rewrite the sign. So we use here that the sine of y is equal to the cosine of y minus pi over 2. This is a well-known trigonometric identity, and it allows us to rewrite this limit. So this gives me 1 minus cosine of pi x of pi minus x minus 1 over 2. So far I've just rewritten the same expression. So now another thing we want to remember is the limit of 1 minus cosine of y over y squared over 2. This converges to 1 as y converges to 0. So I want to write here exactly the same expression. So I want to write pi x minus 1 half, everything squared over 2. And now, to be consistent, I have to repeat this expression here, and here I copy the log. Right, but now you observe that as x goes to 1 half, this guy here goes to 1. Why? Because it's just a consequence of this limit here with the substitution y equals pi x minus 1 half. And you observe that when x goes to 1 half, y goes to 0. So we can use this known limit here. So we obtain that this guy here actually goes to 1, and therefore I can remove it from the limit. So I obtain that this is equal to the limit as x goes to 1 half of the latter part. And now we still have to understand what's going on with the log. And in order to do it, I recall the limit of log 1 plus y over y. This goes to 1 as y goes to 0. So we want to use this known limit too. And in order to do this, I simplify now this expression here. So instead of writing the log of 2x squared plus 1 half, let me delete this and let me write 1 plus something else. And the something else is going to be 2x squared minus 1 half in order for these two expressions to coincide. Good. And now let me just move this guy here on the right. Okay, so far I have just the same expression. So I want to add here and here exactly the same expression in order to use this known limit here. So you see that the y here is nothing but this little expression here. So I copy this one here, 2x squared minus 1 half, and I copy it here too. Good. And now the first factor of this expression converges to 1, thanks to this, with the substitution y equals this expression here. Perfect. So I've just found that this initial complicated limit is nothing but a very simple limit of this ratio. And now basically we are ready to conclude, because this is nothing but x 1 over 2 pi squared over 4, and the denominator is going to be x minus 1 half times x plus 1 half. So 1x minus 1 half simplifies with the numerator, and so I get this. And this limit is certainly 0. Wow, fantastic. So the limit from the right is 0 indeed. And so finally we have that fa is continuous if and only if a times a minus 1 half is equal to 0. You remember we had that the continuity means that these two limits have to be equal to 0. The second one is always 0. So the first one is the only one that matters, and the value of the first limit is this one. So this expression has to be equal to 0, and this is 0 if and only if a is equal to 0 or a is equal to 1 half. So this concludes our exercise. Thank you for watching.